Hey everyone, Gene here. Welcome back to the channel. Today we're diving deep into Java multithreading, specifically focusing on volatile variables and atomic variables. This is the 9th part of the Java multithreading series, so if you're new here or missed the previous video on the Java locking framework, make sure to check it out in the Java Advanced playlist. You'll find the link in the video description below. We'll be creating practical examples for each topic so you can immediately apply this knowledge to your own projects. And stay tuned until the end because I'll reveal a secret tip to significantly boost the performance of your multi-threaded applications. Let's get started. First up, volatile variables. Imagine this. You're working with a shared variable, like a flag, indicating whether a process is running. If one thread modifies this flag, other threads need to be aware of the change instantly. This is where volatile comes in. Volatile is like a special keyword in Java that acts as a memory barrier. It ensures that any changes made to a volatile variable are immediately visible to all other threads. This prevents the dreaded visibility problem, where threads have outdated information. However, it's important to note that volatile doesn't guarantee atomicity for complex operations. For example, implementing a variable counter ++ is not atomic. It involves multiple steps and volatile can't prevent other threads from interfering in the middle. So this raises a big question. When should you use volatile? Primarily for simple read-write operations on a single variable, especially for things like status flags, such as is running, is interrupted, where you need to ensure that all threads have the latest information. Let's see this in action with a quick example. We'll calculate Euler's number while another thread controls the execution time. I'll put the code on the screen so you can follow along, and you can also find all the code examples of this video on GitHub. I'll post the link in the video description below. Okay, so let's create a volatile example. For that we create a new class which implements runnable, and right away we override the run method, and in here we can define what we want. First we define Euler's number calculation. Then we execute the calculation, then we wait for a moment, and then we get the value. So let's then define a method called calculate Euler's number, in which we start by defining the result as big decimal and a counter. Let's also define a while loop, which keeps on running as long as is interrupted is not true. Alright, for calculating Euler's number we need a factorial, so let's create a method for that. So just as a recap what factorial is, if we pass on a 1, it's just 1. But if we pass on a 2, it's 1 times 2, meaning that our result will be 2. If we pass on 3 though, it's 1 times 2 times 3, which ends up being 6. And so on and so forth. Alright, and that's exactly what we are doing here. So we create a for loop, which starts at 2 and runs until to the number that we get as a parameter n. And in every iteration, we multiply what we have times the iteration number. What we also need is an inverse. So just as a recap for that, the inverse is none other than 1 divided by a number that we provide, which in this case is the factorial. This also requires a precision. So let's quickly define a math context for that. And then we are ready to add it to the main result. And the sum of all the iterations in the while loop is the result, which is our Euler's number. And to count around, we use the counter. In this case, counter ++. Now we also want to set the scale. That's a small necessity when we work with big decimal. Then after having done so, we print the iteration count and return the value. Alright, let's go back to the run method and create a new callable, which executes the calculate Euler's number method. Now let's create a new single thread executor and submit the callable to it, which returns a future. Now as long as this runs, we continue here by setting the thread to sleep. So let's create a variable for that, calculation time, and let's set it to 1000 milliseconds. After having done so, we set the isInterrupted variable to true, which also terminates the while loop in the calculate Euler's number method. Alright, now let's get the value, because it's a future currently, but we want a big decimal, and then let's print it. After having done all that, we need to shut down the executor. Now let's go back to the main method and create a new instance of volatile example and run it. And here we can see the huge Euler's number that we just calculated. And we managed to calculate 1400 iterations of it, which is quite fast, don't you think? Now let's talk about atomic variables. Remember how I mentioned that volatile doesn't guarantee atomicity? Well, atomic variables solve that problem. They provide thread-safe operations on primitive data types like integers, long, and booleans. Think of them like indivisible units. When a thread performs an operation on an atomic variable, it happens as a single, uninterrupted action. No other thread can interfere, ensuring data integrity. Java provides a set of classes for this, such as AtomicInteger, atomic long, and atomic boolean. These classes offer methods for incrementing, decrementing, comparing, and setting values atomically. Let's create a more advanced example where we leverage the power of multiple CPU cores to calculate Euler's number. We'll use atomic variables to coordinate the work and gather results efficiently. Okay, time for another example, this time the atomic example. So let's create a new class for that, which also implements the runnable, and right away we override the run method, in which we define what we want to do. So we want to remember the start time, then we define the Euler's number calculation, then we execute the calculation, then we get the values, and then remember the end time. So let's commence by remembering the start and the end time, and by calculating the milliseconds in between both times. In this example, we also make use of callable to calculate Euler's number, and for that we also create another method, calculate Euler's number, which returns a big decimal. In here we also want to remember the start time, then we get the calculation range, so basically just a certain range between the iterations. Then we calculate that range, then we set the result to a certain precision, and then we remember the end time. Now for both of these times, we make use of instant again, and then we calculate the duration in milliseconds between them. Now let's go to the calculation range part. Here we define the result as a big decimal, and we also make use of a counter, which in this example is an atomic integer. We also need to define the size of the calculation, meaning the iterations per packet. So let's set that to 300. And this is what we put into a variable that we call last iteration. And we also need a first iteration, which is the last iteration minus the iterations per packet. Now let's move on to calculate that range. For that we're going to make use of a for loop, which runs from the first iteration until to the last iteration. And then in every iteration we calculate the factorial. For that, like in the other example, we create ourselves a factorial method. And then we also need the inverse, which also requires to set the precision. And then in every iteration we add to the result whatever inverse comes out. Let's also add a second counter, in which we count every iteration in here. After having completed all the iterations, we need to set the scale, which is this little must that we need to do when working with big decimal. Now let's add a little bit of statistics. For that, let's create a new variable of type long accumulator, one for the minimum duration and one for the maximum duration. And let's also add a long adder for getting the total calculation duration. Alright. So let's accumulate for min duration and also for max duration and also for total calculation duration. And after having done that, we print the calculation duration that we took in this thread between the first iteration and the last iteration. After having done that, we return the result, which brings us back to the call method within the callable so that we have something to return. Alright, now let's go to the execute calculation part. The first thing that we want to do here is get the available processes, which is none other than the number of CPU cores that we have. And this number is what we provide to create a new fixed thread pool, which returns to us a new executor service. Now, because all the callables will be returned as futures, let's create a list for that, Euler's number futures. Now let's create a for loop, which starts at 0 and runs until thread packets, which we set to 20. Meaning that it is 20 threads that we create. And now in every iteration, we submit one Euler's number calculation to the executor service. And the result of that is added to the Euler's number futures list. Now let's put our efforts to getting the values. For that we first create a variable Euler's number of type big decimal, in which we add all the results of all the futures. So this will be our final Euler's number. And after having done all that, we print it to the terminal. And last but not least, we print all the statistics that we created. Alright, that's it. Now let's go back to the main method and create a new instance of the atomic example and run it. And the first thing that we see are all the threads and the duration that they took for calculating their part of the Euler's number. After that we get the Euler's number itself. And last but not least, the statistics. So in total we calculated 6,000 iterations. The fastest thread was done after 1 second, and the longest one was a bit more than 7 seconds. So the total calculation duration was 88.4 seconds, but due to multithreading we just spent 8.5 seconds, which is pretty impressive when I see it here as a number. Now it would be interesting to see the same results on your computer, so feel free to post your statistics in the comment section below. That's a wrap on volatile and atomic variables. I hope you found this helpful. Don't forget to drop a like if you enjoyed this video and learned something new. And subscribe to the channel to stay updated with the next video in this series, where we'll explore the fork join framework, a powerful tool for parallel processing in Java. Thanks for watching and happy coding.